Hi everyone, I hope you're doing well. This is lesson 3, the last type of transformation for functions, and this is stretches, sometimes also called compressions, but we'll talk about it as we go through. So I'm going to go kind of quick through here, so if you need to pause the video, just go right ahead. So the first thing we're going to look at is what is the effect that this thing in front of a function does. So I'm just going to highlight a couple things here, the 2 and then the 1/2. Just recognize that this is like having 2 and then in a parentheses, I have the actual function. So we'll start with the parabola because most people are familiar with that. So I'm going to fill in these key points for the base function. So here's my base function of the parabola. So these things you're probably getting familiar with now. These are my key points. And so if I was to plug these in, how does that affect the function? We often call this value a. So as long as it's in front of the function, we call it a. We saw that with reflections. So in this one, if I was to put a 2 in front, it's like 2 times this value. So if I plugged in -2 squared, that would get me 4. So I would have 2 times -2 squared. So that would become 8. Similarly with the next one, 2 times -1 squared. That gets me 2 times 1, which is 2. And then I'll just quickly go through these. So it's stretching the function vertically by a factor of 2, we would say. Similarly, when I put a half in front, I'm going to have 1/2 times -2 squared. -2 squared is 4. 4 times a half. I get half of the original 4, and so I get 2 as my y value. And this is going to happen for all of these. So this becomes 0.5, this will be 0, 0.5, and this is also 2. I'm just going to circle this and change the colors because I'm going to graph these. Oops. If I can. Oops. Graph these on our function, on our grid here. Maybe I won't do that. Okay. So I'll graph the green one. And you can do this. And again, I'm going to kind of do this quickly. So you could pause and try this yourself. So this is y equals 2x squared. And then I tried to do this in a different color, but I'll just do it in orange here. It's this one. So this is what this one looks like when it's 1/2 in front. So hopefully you can notice in comparison to the original, and I'll plot it quickly, this is the original y equals x squared function that has not been stretched or affected at all in any way. And if you look at the green one, it's vertically stretching it. So it's like it grabs it from the top and bottom and just stretches it out. Similarly with the 1/2, it's like it's been stretched by half, so it's growing half as quickly. So what we say in general is that this a in front of a function creates a vertical stretch. And we would say a vertical stretch by a factor, because it's multiplying, so that's a factor, of whatever that a is. So if it's a half, 2, 4, whatever it happens to be. And we're going to see when we change our key points, and that's really what we're focusing on eventually, is that the points x, y becomes x, and then the y value I've multiplied by the a. So this a translates into the a in front of the function and changes each point. So for example, this 4, if I just highlight this, I multiplied it by 2 because there was a 2 in front, and then I multiplied the other one by half. So 4 became 8, and in the other function it became 2 because I multiplied by a half. What gets a bit trickier is when this value is inside of the function. And so notice here now, this 2 and this 1/2 is inside of the brackets. Now I'm going to call this thing something else because it affects it differently. And we call this the k value. And so when I do this one, we'll again take our key points. Notice now I'm plugging in values that where the x values here are half as much. Even though this is 2, it's like I'm dividing by 2 for my x values. And what happens is if I plug this in, so I've got bracket 2 times -1 bracket squared. So inside that bracket is 2 times -1, which is -2. -2 squared gives me 4. I do this for the next one. This will be 2 rather times -0.5. And so 2 times -0.5 is -1. -1 squared gives me 1. All of these y values remain the same as the original y values of this in blue. So they're not going to change. And similarly with this next one, I'll change the colors this time. I have 1/2 in front, but notice I've multiplied all of my x values from the original ones by 2. Even though it's times 1/2, the effect is that it affects it in the opposite way. So this becomes 1/2 times -4. Well, 1/2 times -4 is -2. -2 squared, I get a y value of 4. Similarly, I have 1/2 times -2. That's -1 squared. That just gives me 1. These y values, again, remain the exact same as the original key points. And so the effect here is, in general, we say that this is a horizontal because it's affecting the x values now if it's inside the function. So it's a horizontal stretch by the inverse, 1 over k. And each point, xy, becomes x divided by k. So it always flips it. So if it's dividing by 2, it actually multiplies the x value. If it multiplies the x value, then it's dividing by 2. It's very strange, but this is the effect. Visually, especially with a parabola, we don't see much of a difference between this and a vertical stretch. They're actually pretty hard to distinguish. Oops, that should be over here. So there's my original. The green one, -1, 4. It kind of looks like a vertical stretch, I think, but what's actually happening is it's compressing it horizontally. If I could show you visually what I'm doing with my hands, it's like I'm pressing this green function together. And so this would be this function of bracket 2x bracket squared. And then the other one, -4, 4, is a horizontal stretch by a factor of 1 over 2, but we flip this, so it's really a stretch by 2. And so this one, -2, 1. Similar here. Again, it looks like it's been vertically compressed, but what's happening is I'm actually stretching it out horizontally by a factor of 2. So very strange. For the k, and the k I think becomes the trickiest part to remember in this unit. So in general, if you have a value in front, I consider that an a value, and if I have the value inside, I consider that a k. So this is a, and this is deemed k. And they do different things. One affects the y values and the other affects the x values. So this is the case for all functions in general. So we generally say this, and you now have all of the components a, k, d, and c. And just remember, a and c affect the y values. And k and d affect the x values. And one, if we go back to the a and c, a multiplies the y values and c adds or subtracts to the y values. So in general, if I was to write this general formula into the actual equation for a quadratic, it looks like this. And it looks messy, but it's like a, then bracket k, and that's factored out from this bracket plus c. And I throw on the squared outside of those brackets. In the square root function, it's like y equals a in front and then a square root. The k is inside the root, factored out from the x minus d, and then outside of the square root I have the plus c. And then the last one, which is the reciprocal function or the rational function, you can write this actually in a couple ways. There's the a in front times 1 over k is down here, as well as d, and then plus c. Or sometimes it's just written like this. You could simplify this so a is on top, k, x minus d, and then plus c. Either way for that one. The more familiar you get with these things, the easier this is going to be. So let's just look at some equations. A lot of these are just kind of tricky ones, but it's good to deal with them right off the beginning. The first one's pretty easy. If I was to describe the transformation on the base function, it doesn't matter what the base function is, it could be anything really, and we'll look at a few examples. But if I throw a 4 in front, and it's not inside the brackets, and it's multiplying, it's really 4 times the original function f at x. This makes this an a value. I could describe this as a vertical stretch by a factor of 4. Easy. The second one is a bit trickier. This is like x over 2. That's kind of cut off there for some reason. But this is the same as f at bracket 1/2 x. Just written, simplified together. This means that I'm dealing with a k value because it's inside. So I would say k is equal to 1/2. And the strange thing is, if its k is 1/2, this creates a horizontal stretch, we would say, by the flip of that, which is by 2. And it will always be the flip. So like the next one, this has a 3. Obviously this is inside, so that's k equals 3. And I would describe this as a horizontal stretch by the flip, which is by 1 over 3. And so it's actually, in a way, squishing the graph, whatever that graph happens to be. So a couple other tricky ones. This one, I've got a quadratic because it's x squared. This could be written, really, it's kind of like this. 1/4, and then the x squared, and you can put the squared in or outside of the brackets. In this case, it doesn't really matter. But this becomes really like this. So it's just been simplified. When it's written the second way, I think it's more obvious, but this makes this an a value of 1/4. And I'm showing you these tricky ones just so you have them. You're not always going to have tricky ones to deal with, but it's good to look at them, I think. So this is a vertical stretch by 1/4, so by a factor of 1/4. Another one, root x, so obviously we're dealing with a radical. This could be simplified, or thought of rather, by 1/3 and then times x. And so this is obviously inside or in this case the root, where I would say k is 1/3. And that makes this a horizontal stretch by the flip of that, by 3. And then the last one, this is the same as a rational or the reciprocal function. This can be written in 2 ways, 2 times 1 over x, or just put the 2 up top. And this is often just considered an a value. And I'll talk about this one more in class when we're together, but in the end, it doesn't really make that much of a difference. It actually could be considered either. So I'll just say this is a vertical stretch by 2. Great. Okay, so let's, now that we've got the exceptions kind of out of the way, let's go and try to graph some of these. So we're going to always use our key points for the base function. So my base function here is y equals the root of x. So I have to always go to that, decide that, and then get my key points. We're going to take that thing and we're going to do this to that function. So when I think of that, that's the same as writing y equals 2 and then the square root of x. So this makes this an a value because it's out front. So my original function, y equals root x, I have my key points. So 0, 0, 1, 1, 4, 2, 9, 3. Again, key points here. Starting to get used to these now. I want to transform those key points by affecting them with this thing. And it's always going to be 1 over k times x, comma, a times y. So in this case, there is nothing affecting the x, but there is 2 times the y. So I'm going to take all of my x values, they're going to remain the same. So those key points don't change because there is nothing affecting x. But I'm going to multiply the y values by 2. So 0 times 2, 1 times 2, 2 times 2, and 3 times 2. So this is a vertical stretch. So the original, just so we see it, it looks like this. Notice I didn't use a large scale here, and that's okay. But now I'm going to take that graph, and I'm multiplying all of these by 2 vertically. So this is y equals 2 root x, and this is y equals root x. Like that. In the next example, this time I've got a 2 inside the function. This is the same as writing y equals root 2x. So base function, y equals root x, because that was what we were told at the beginning. My key points. And now that 2 has the opposite effect. Because it's 2 times x, I actually am going to do x over 2. Again, that's this strange thing that happens. The y's don't change, but the x's are actually divided by 2 when it's k. So I'll just write in the y values because I know they're not switching. And I'm going to divide all these x values by 2. So I got 0, this will be 0.5. I'll put it into decimals where necessary. And that one, 9 divided by 2 is 4.5. So I can sketch these. And I can actually get the last point on here. Right there. And so I got y equals root 2x. So a and k, good to try out. Let's try a couple more with different function. So this time, sketch the following curve families, they're called, because they are related. So the first one, I have 2 over x. So both of these, the base function is going to be 1 over x. This is the same as y equals 2 times 1 over x, which makes this an a value. Again, feel free to pause at any time if I'm going a bit too quick. I'm going to put the key points for my base function 1 over x. These ones are actually fairly easy, -1, -1, and then 1 comma 1. And don't forget your asymptotes, y equals 0 and x equals 0. So these are my key values. They're not all just points. So I'll call them key values to include when I'm going to transform them. The a value is going to affect those. Do this in green. By multiplying always the y's. So my x's stay the same, -1, 1, x is 0. But my y's I multiply by 2. So I got -2, 2, and 0 times 2 just remains 0. So if I try to sketch that one, so I'll just throw my -1, -2, just watch your scale here, it goes by 0.5s, and then 1 comma 2. And then we generally put in the asymptotes as dashed lines to help create those barriers where this function isn't going to cross. So I have something like this to sketch. So it's never going to cross those. So we should show it going down or to the left or right or up, but never hitting that function. So this is y equals 2 over x, or you call it f at x equals 2 over x, either of those. The next one, notice this one is now in the denominator. So this makes this a k value. So k is going to be equal to 4. That means I'm going to take x and I'm going to divide it by 4. My y values don't change. Again, I'll change this color. And my base function, 1 over x. And my key points, just copy those from the previous one. And I'm now going to divide the x's by 4. So this becomes negative 0.25. My y value doesn't change. This one becomes positive 2.5. And when I divide 0 by 4, it just remains 0. So my asymptotes aren't going to change on this. So negative 0.25, comma, negative 1. So tricky to get that in there. And then this one, and then my barriers, the asymptotes, like that. And we'll just connect. So we show where it's going, like that. Label this y equals 1 over 4x. Great. So one last example, which is just a general function, and we did something like this earlier in the unit, and we're going to transform this function, these series of points, by doing this to it. So this is, again, a little bit of a tricky one to do, and try to show these just because I think it's good to get them out of the way. F at x over 3. This is the same as having 1/3 times f at x. If you see it that way, I think it's more obvious. That means this is an a value of 1/3. So I'm going to take all of my points. X is not going to change, but I'm going to multiply the y values by 1/3, or divide them by 3, whichever you'd prefer to think of it. So my x values don't change, but I'm going to divide these by 3 or times by 1/3. So 0, that actually doesn't change. 3 times 1/3 is 1. This becomes 3 times 1/3 as well. This one becomes 0.33 repeated, negative 0.33 repeated, and then the last one, 0.33. You could put them as 1/3. That would also be fine. So if I sketch this, that doesn't change. This one does. This one does. I'll kind of approximate where 0.33 is. So basically, and now I try to copy that same shape. So a bunch of lines connecting these points. Everything has been squished. It's a vertical stretch of 1/3. So I would label this, what do they call this? G at x. Like that. Great. Okay, try the U-try. I'll throw up the solution in the notes. This one's a good one to try. So you can stop the video now, or I'll show you just to get you started what to do. It's up to you. This will be my A value. My K value is 1/3. So if you describe these, that means you've got a vertical stretch by 3 and a horizontal stretch by also 3. So you flip it. So the 1/3 becomes 3. And we're dealing with the base function here of a square root x. So y equals root x. So I'm going to show these points. So x, y, 0, 0, 1, 1, 4, 2, 9, 3. I'm going to transform those. So beside this, I'll do this by multiplying the x's by 3 and multiplying the y's by 3. So all of these x's get multiplied by 3. So I get some bigger numbers, and same with the y's. And then you're going to plot those. And you kind of want to take your time with this part, no rush. And I tend to just connect in a curve in multiple stages. And so this is my, what they call it? J, is that? Let's call it J. J at x equals 3 root x over 3. And just to compare it to the original untransformed function, it looks like this. That's y equals root x. Great. Okay, try the practice questions, and if you have any questions, come to Extra Help, or you can ask them at the beginning of next class. Okay, take care.